That worked better before lunch, but that was still pretty good. Well, thanks everybody. We're starting off our afternoon sessions here. This one's about linkages between economic models. That's capacity expansion, production costs, and resource adequacy. We have Bethany Frew from the National Lab of the Rockies chairing this session. Bethany and I also go way back. Bethany is an expert on markets. She's done a lot of capacity expansion work. She's also the co-chair of eSig Systems Operations and Market Design Working Group. So please come talk to Bethany if you're interested in any of those areas. And Bethany, go ahead, take it away.
Thank you, Drew. Good afternoon and welcome to the post-lunch session. Hopefully we'll keep you all awake during this. I think we have a very exciting session lined up for you. So just to kind of get the blood flowing again, raise your hand if you have or currently do work on linking capacity expansion models with either resource adequacy or production cost models. Okay, so roughly half, 2/3. Okay, so for those of you who raised your hands, this session is directly relevant to you. If you didn't raise your hand, hopefully you will learn something new that will inform the rest of the work that you do on the power system. So there's a couple of themes in this session that are going to tie back to content that we heard earlier this morning. If you heard Paul Denholm's great opening remarks, a keynote speaker, he talked a lot about interoperability and improved modeling capabilities. And so we're going to hear about that in this session. As Drew mentioned, linking capacity expansion with resource adequacy and production cost modeling. So we're really talking about that planning timescale. But there was a session back in Tucson, if you were at the March eSig workshop, that focused on that linkage between resource adequacy and capacity expansion modeling. So we're really kind of building on and expanding from some of these themes and previous content that we've heard today, but also in previous eSig events. So our session today has 5 speakers. They come from backgrounds in software development, analysis, and just generally thought leaders in this space of linking tools and data together. So we're going to start, I think that the arc of this session is really to kind of have a foundation of what do we mean by interoperability? What is this whole idea of linking tools and data? What does it look like? So kind of thinking about the mechanics of doing this. And then we're going to, as we kind of move through the speakers, we're going to get to some more specific applications of how we can link different tools together. So hopefully that'll be a nice progression for this session. So without any further ado, I will start with our first speaker, Hazem Abdel-Khalek, who is the co-founder and head of tools and data at OET, which is the Open Energy Transition.
Thank you so much. Very good pronunciation of my last name. Doesn't happen all the time. So thank you about that. Yeah, it's here. So I decided to go with the title Interoperability between models, the next bottleneck in energy planning, but then I quickly realized a little bit later than the time I could actually change the presentation is that the next might not be the best term for this. It's actually the current bottleneck as we see it. And just to try and set the scene for the next presentations, I'll quickly go through what I think is the current situation. So I think we already have so many different models very good at addressing the questions. And in that sense, I think we've more or less solved the energy modeling or energy planning problem. However, what we see now more predominantly is the integration of different tools. So linking different tools together, making sure the data flow is consistent and meaningful and so on. So in that sense, I'm going to talk about what interoperability is. I think Paul talked about it briefly in the morning. He said he doesn't like it. In contrast, I do like it, but I think we need to have some sort of a definition that we all agree on. So that's what we're trying to do today quickly. Yeah, I think we don't need to get into the details of here. We all know that how energy planning has become more and more complex question, especially with the introduction of variable renewable energy into the systems. And what I think is really important to always keep in mind is that the modeling domains have been more than ever interdependent. So for example, if you want to answer a question about capacity expansion, for sure you do need a lot of information from the climate data. And as some speakers said today in the morning, while one could use one representative year, this is not always the best option to go because you might have some outliers or some weather dependency that completely changes the picture for capacity expansion. So in that sense, I think we could also agree that there is no one silver bullet model that could answer all the questions. So to one degree or another, we do need to link different models together to cover this full-scale problem. And in that sense, what we've identified in the past is that usually the problem is not about each individual model. Of course, there might be some shortages between what one model handoff and what the other model would expect, but the main issue is usually about this handoff step. Whether it's or maybe before that, we can talk about very simple workflows. I think today in the morning we've seen very complicated workflows. I think one of them had over 25 different boxes, so I'm not going to go through all the different examples here, but just maybe the first two. If you think about plant flexibility, in that sense, we would not only talk about a plant or a unit-based model, but that would then feed into a production cost model, just as an example. And another way to just talk about climate impacts, you would not only need a weather model, but also, or a climate model, you would also need capacity expansion model, and in very different cases, also production cost model. While this session is focusing on economic models, but the term interoperability not only tackles this, but also models beyond the scope of economic models. So the one on the right also touches upon engineering models like power flow, but we will try to keep the session towards more the economic models. So back to the point Paul raised in the morning, what is interoperability? I remember he put it between quotations. One way we can think about interoperability is that it's the ability to connect independent models and domains to exchange, interpret, and I think interpretation here is one of the very important terms, and use information consistently in a coordinated analysis. The way we perceive interoperability is that it has three different dimensions. One could argue there are more, but I think these three more or less cover the different aspects of it. The first one is the technical dimension, which basically is, are we able to take the information from one model and give it to the other or not? So basically, this could be CSV files manually handled by the teams of different models. That could be XML files, could be APIs, could be many different things. Second dimension is the semantic dimension. And in that sense, and in our experience, this is the part where most of the issues come from. Is the data interpreted properly between model A and model B? Because, I mean, I'm coming from Germany, so you haven't given enough background about open energy transition, but I've realized throughout the presentations today that most of the presenters are from the US or presenting US relevant problems. And I can just remember 3 years ago when I was introduced to the IRP initials, I had no idea what that means because it's not really a term that we use in Europe. That's just one example about the entire problem that might not be easily linked to different geographies as just one example. The same happens for units, the same happens for the definitions of different terms within each model. And that's why I think the semantic part is one of the important aspects of interoperability. And finally, the governance dimension, which if we try and summarize it in one question is, can this data that flows from one model to the other, could it be trusted and how is it maintained? And this is especially relevant when the different tools are not coming from the same vendor or from the same company. Now then becomes the question of who takes charge of linking these models, who will maintain it long term, and who will be able to adapt it as new versions of each model come to light. So what could go wrong? I think many things could go wrong. Many things go wrong all the time, especially when we do manual data handling, which takes me to the first point. So on the technical aspect, one thing that I've seen, especially talking to different data partners when we try and work in a consortium with different companies, and in the end, we would like to answer just one question. The amount of time we put into building these ad hoc workflows between a climate model, for example, or a demand model to a capacity expansion model, this takes the majority of the time usually. And in that sense, the manual data handling always poses problems. So it could be that the data don't match, or someone does manual data handling and then forgets leap year, for example, or daylight saving, as two examples mentioned today in the morning, or that the workflow breaks if a new version of one of the tools is released. On the second dimension, the semantic one, one thing we've seen is just the different units that one model uses compared to the other, even when they do very similar things like capacity expansion modeling and production cost modeling. And on the governance side, this might also be a very tricky one because we're not always sure who is going to maintain the tool long term. But I think what makes it easy is not on the technical side is to try and standardize the interfaces and automate the workflow. One thing that has been going on in the ecosystem for quite some time is to develop a data schema or a shared data schema that different models could use. However, it hasn't been very successful in the past a few years at least. So that's one of the things that we hope could be done in some of the upcoming projects. On the semantic side, one thing that we would need is a shared definition, common metadata, and aligned assumptions. On the governance part, it's more towards making sure it's clear who owns these translators and how is it documented, and it makes it always updated with the new versions of each tool. That takes me to the last slide. One thing I see would be useful in this sense is the use of open source. That's something that we do at Open Energy Transition. We promote and build open source tools, and I think it's a good slide to end on because open source could be playing an enabler role for these tools, especially if the different tools are from different vendors. So in that sense, the shared infrastructure could be open. So the engines themselves of the different tools could still be proprietary, but the linkages between them or the bridges could be open source. But because time is running out, we can take a bit more about these on the questions. Yeah, the way forward, I don't think we have time for that, but we can talk about it in the questions part. But in general, selecting a priority workflow would be a very good starting point. If you do know that there is a specific data handling schema that makes sense to start with, we can start with it and then formalize it and see which parts of these could be reused. Thank you so much, and back to you, Bethany.
Thank you, Hazem. All right. Next up is Norm Richardson, who's the Vice President of Modeling at Yes Energy. So he's going to go one layer deeper than what we just heard, kind of that overarching nice foundations that Hazem just went through. So Norm is going to talk about a model that he helped to build called Encompass, and talk about some of the things to look out for in the workflow with that tool.
All right, thank you, Bethany. Much like Paul mentioned this morning, I'm one of these guys, and I feel like I'm in good company here that loves modeling, that has done it at least, for maybe 5 or 10 years, either as a software developer or as a data vendor or as a consultant. My latest endeavor, as Bethany mentioned, has been developing the Encompass model, which I like to think of it as the name would imply and covers a lot of these aspects that would be linkages in there in terms of capacity expansion, production cost, doing some market analysis and resource adequacy. We have several users that employ Encompass for developing integrated resource plans, for doing production cost analysis, reliability, and analysis as well as part of that. But of course, the reality is, you have, even within one tool, if you were to do all of those things, there's still a lot to think about in terms of data linkages and handoff. It becomes maybe a little bit more complex when you start talking about different tools from different vendors. But even when we're providing this same type of modeling that could do everything. The approaches are very different. The applications are somewhat different, and they're done in different phases. And so that's going to really be the focus of my presentation here. And like any good engineer, I'm going to recycle previously used material and just kind of highlight from this where I think it relates to the topic that we have here today on the panel. In my mind, what we're talking about in terms of really capacity expansion and linking all of these aspects together, of course, is the three objectives that most resource planners or transmission planners have in terms of what's now really can be summed up as affordability, keeping the prices as low as possible, the reliability aspect in terms of keeping the lights on. And although it comes in and out with various administrations and different regulations, it is also a look at some type of decarbonization, sustainability, and other practices. And just like in software development, there's the old axiom, you can either have it cheap, fast, or good, pick any two of those three. And a lot of times with resource planning, you're picking two out of these three to really focus on. But what this does is it kind of outlines what's the problem that we're trying to solve, how is it complex, and then how can we take those various components and come up with something that really encapsulates at least a good portion of all three of those aspects. So the real problem here is you've got all of these things that you want to take into account, but as much as we would have these breakthroughs in processing power, in AI, in hypercloud parallel computing, the problem size is just really too big to do all of this at once. And as an illustration, from a capacity expansion standpoint, we often need to take a long-term view of what we're doing. We'll have, in many instances, either at a state, a regulatory, or a corporate level, goals that are going to decline year over year, in some cases drastically, where you have a big target coming up in 2035 or 2040. And so your resource planning decisions, your capacity expansions decisions that you make in 2030 have to be informed by what's going to come into the future. We also have where tax credits are going to expire, or we have some type of maturing technologies, long duration energy storage, small modular reactors, where we may assume some type of a learning curve where the cost and the time to deploy those is going to start coming down up to a point, and then they become commercially viable. And so in our modeling, we may want to take a view that, yeah, if we wait a little while, the price is going to get cheaper, it'll be easier to deploy, but when do we want to do that? So we need to take a long-term view with a lot of our capacity expansion decisions. But we also then need to be able to look at that not just over what we think is going to happen, but over the realm of uncertainty, particularly around weather, to get to the resource adequacy and the resiliency aspect of the power grid. And that's going to include incorporating things that we know are going to occur in reality. We just don't know when or how often they may occur. And that would include the multi-day droughts for renewables that could happen. We have the ability to maintain some ancillary services as part of that. Traditionally, a lot of the capacity expansion models really oversimplified this and didn't consider the reserves. But of course, this becomes a very important aspect to be able to capture how do I account for that uncertainty around weather in terms of my resource expansion decisions. And ultimately, we're going to come back to some type of reliability target. And in many instances, we're going to use something like a Monte Carlo-based analysis to quantify, have we met that reasonable target? In many cases, it is that 1 day in 10-year loss of load expectation that we want to meet. So we add all of those objectives into our capacity expansion decision. And really what we want to do is throw all of that together and come out with something that's affordable, that's reliable, that meets all of our objectives at once. So that's really the wish list. And really what I usually come back to is that at some point, you're going to have to break up this type of problem. And so these are the big chunks or the aspects of an integrated resource plan or an integrated transmission plan that have to be incorporated and looked at. So there's the resource adequacy, which in a lot of cases is really kind of you're feeding it what that 1 day in 10 year or whatever your LOLE or other reliability metric is. And often you're going to want to translate that into either a market mechanism or some type of a linearization that most of the capacity expansion models can happen. And that usually takes the form of some type of a planning reserve margin. It could be annual, monthly, quarterly, biannually, depending on the market, and some type of representation of what the ELCC is, either as a static number for a given year or in many instances coming up with some curves or some surfaces that dictate how that reliability could change as you start adding to the portfolio mix. The Monte Carlo analysis, as I mentioned, key driver for determining what that reliability is and what those targets should be. And then very often what we'll do is feed that into a capacity expansion model and say, this is the metrics that we have to meet. Now, the data linkage is there. The resource adequacy modeling doesn't have to worry so much about cost. It really is focused more on what's the outcome of load and renewables and my reliability of my resources to be able to get me to that. So capital cost, production cost, not as important. Don't really need to worry about synchronizing that. But in our long-term optimization, we'll often have a typical meteorological year, which should at least be consistent with some of the history that or some of the forward-looking views that we used in the resource adequacy. So that's a little bit on the handoff there. Because our long-term optimization kind of can gloss over some of those multi-day droughts and do a lot of time aggregation, we may need to do a second phase of that and say, okay, we have a build out that gives us our long-term goals, but we may have some reliability events because we oversimplified the problem to take that long-term view. So in many instances, a midterm optimization where I might say, put a little bit more resolution into how many hours or how many different scenarios I look at, but maybe shorten up my forward-looking time horizon using what I came up with in the long-term optimization as a guide for that. And then finally, I'm going to come down to some type of a production cost or some type of a real operational model. And then at which point I can go back and check my reliability statistics and make sure that I have met my goals there along the way. And of course, this is an iterative process. This slide is really just meant to illustrate some of the challenges, particularly around wind modeling, that comes out with the capacity expansion and reliability analysis, where to do that long-term view on capacity expansion, we often need to do some type of a time aggregation, and we lose a lot of the reliability dangers that underlie the aggregations that we take there. So the fact that we have made some of those assumptions in our long-term view means we've got to account for them at some other level. And so these are the data linkages and the handoffs that are going to be important as part of this. And I'm just going to skip over into kind of my final thing in terms of what does that mean in terms of the handoffs, as well as what type of views that are often made. There's a long-term view, again, for our capacity expansion. No one wants to really make a decision that's just looking at 1 or 2 years in the future. It needs to be making sure that we have our long-term views met while we're able to do something that really accounts for what can happen in the next day, in the next week, as we start to go operational with those. And I've just laid out here a few of the key parameters in terms of how that might change and some of the modeling parameters that might change. For instance, and the last one I'll point out is that carbon target, where you might have a tight carbon target, and even if you're using all of the same tools in modeling, you're going to want to change those assumptions so that your long-term view that had that simplified wind shape, you better hit more than what your carbon target is, because you're going to need to have some type of reliability backup. So as you go through and add more detail, you can actually get a little bit more lenient, but you've got to have a more stricter carbon target to be able to meet it operationally in the future. So even without worrying about coming from different products or different different solutions, even within a single modeling framework, there's a lot of data assumptions that need to be changed or that need to be consistent through this process. So thank you very much.
Thank you, Norm. All right, up next is Russ Philbrick. Russ is a longtime attendee and supporter of eSig. He's the CTO and CEO of Player System Optimization, and he's going to be giving us some, I guess, thought-provoking content that really focuses on engineering principles and fundamentals as it applies to these integrated workflows.
Yeah, I'm pressing.
So,
I don't know.
did I do something? Just
I'll do it here. If I
oh,
can.
it's
It's frozen.
let me see.
I jinxed it. Lacey's going to blame me. I'll just start real quick. So linkages and data translations between economic models. So Hazem and Norm have both identified that this can be challenging, but it's all the more challenging if we don't have common physics between those different models. And I would say that one of the problems is that we haven't done the good engineering to represent that physics properly. I'm going to give you some, whoop, we're way, yeah. So I'm an optimization guy, a modeler. I love making things better, making them faster, figuring out how to get the things in there. And there's a few tricks that we've learned over the years. I'm going to share some of those with you. So take notes, you guys can use them. But the goal here is to help solve the problems the right way with accurate answers and in practical timeframes. And I'm going to focus in particular on the issues of operational flexibility and deliverability of power, which means how do we get that represented in production cost modeling, in capacity expansion studies, in resource adequacy? Because a lot of the barriers we have now are because we don't have the same physics in those models. The representation of power flow, zonal models versus nodal models, for example. And because of this, we're missing the answers that we need that are going to impact the reliability and costs of the system. When I was preparing this last week, I came across this. Some of you others may have seen it also. The market monitor PJM said in 2024, they had $1.8 billion of congestion costs. Last year, 3.2. In the first quarter of this year, 2 billion. And even though it's probably not a fair statement because of some events that happened in the first quarter, it's on pace for 8 billion. Where does this come from? Are we correctly understanding the impacts of the transmission limitations on the way we operate and plan the system? I would argue that we're not doing a good job. And part of the reason we're seeing this is because of our planning processes. So what do we want to do? We want to be good engineers. We want to make good decisions. We want to be efficient with what we do. It's not just enough to be focused on reliability and say economics doesn't matter. And it's not enough just to get the job done without worrying about whether the lights stay on. So if we look at where we've been, a lot of our practices are still rooted in the past. We came from a world where we had isolated utilities that were kings in their domain. They could build the transmission to not have congestion internally. And it was only issues with your neighbors that you had to worry about. So copper plate models, zonal models. We're still doing that today. And it's one of the barriers that we have towards doing the kind of planning that's necessary to capture what matters for reliability and economics. So I would argue that we have a number of incorrect assumptions about what is practical and what is not. I've had folks, maybe even some on the panel here, say that nodal modeling takes 100 times longer than zonal modeling. And I would argue that's only true if you don't do the good engineering to model nodal models. That you can't model long duration energy storage without full chronology. Well, that misses what you're trying to do with long-term energy storage, which is to manage variability over long time frames. And if you address that problem directly, you can solve that problem. Co-optimizing generation and transmission expansion is important, but not practical. That kind of goes back to the nodal modeling problem. If you get the nodal modeling problem solved efficiently, then it becomes very practical to do nodal capacity expansion. Resource adequacy also is not practical for nodal. And, This is my old set. Oh, well, I didn't mean to say ELCC is wrong. My apologies. But it's no longer needed. ELCC is really like LMP. It's a good signal for what happened and what things are worth, and it's a good mechanism for compensating. But it's a terrible mechanism for doing capacity expansion. And it shouldn't be part of the resource adequacy world except as an outcome to help compensate people appropriately. So I'm going to focus quickly on 3 areas that we could provide better engineering to give better outcomes. Flexibility, DC power flow, and chronology. So I'm going to go quickly through this just to give you a couple of ideas about how to do these things better so that we can do the right physics in all these different models. So the first thing, flexibility. I think we all understand that the longer in advance we have to make decisions, the more uncertainty we have. And as we get closer to real time, the less uncertainty. The problem is, as we get closer to real time, we also have fewer choices. We have less flexibility. And the control room faces the challenge of balancing flexibility and uncertainty at all different time frames. And that is also true in the long-term planning models that we have to deal with. And so our goal is to represent this balancing act that operators have to deal with. And we can think about that as recourse and non-recourse decision-making, making use of the decisions that you have, the decisions you have to make today, because if you don't make them today, you're not going to have them tomorrow, and keeping in your pocket those choices that you have for later to deal with the things that you're going to get wrong. And how do we do this in a modeling framework? Well, we want to operate the way we want to simulate the way the system gets operated, which I would describe as a rolling horizon process with multiple decision cycles, with feedbacks from the long-term decisions to the short-term decisions, and feedbacks in real time from the short-term decisions to the long-term decisions. When a forced outage happens, it feeds back into unit commitment of day ahead and intraday, right? And so this is how the system actually works, and this is how operators manage uncertainty through ancillary service procurement and other flexibility mechanisms to make sure that you have those choices available to you. So that's lesson number 1. Model flexibility the way it happens in the real world. And this also applies to different time frames. We could think about the same thing with long duration energy storage and long-term capacity expansion problems. DC power flow, number 2. Many of us, I did not go through a power systems program. I came to this through a different path. And so I'm learning things without being taught in school what I should believe. And one of the things I've discovered is that most power system folks get taught that the B theta formulation of power flow is necessary. And that is true if you're dealing with AC power flow. And it's also appropriate if you absolutely need to solve power flow in every single branch and constrain them at the same time. But that's not the way we solve the markets today. And that's not the practical approach. Instead, we need to focus on what are the constraining elements that actually matter. Because in the end, at any moment in time, if you look at the PJM market, for example, there's maybe a couple of dozen transmission branches that are binding at any moment in time. If you know what those 2 dozen are, you can ignore everything else. And so the art here is to model what you need and include that in the optimization and not include everything. So to improve DC power flow, we have to figure out what those are and include them in our models and not include the things that don't matter. And so the real trick with DC power flow modeling is security analysis. How do you figure out what that subset is? If you can do that efficiently, then power flow nodal modeling becomes very practical. And then finally, chronology. The role of chronology in models is to represent the variability and how that impacts the outcomes that we care about. And that's true for real-time production cost modeling or long-term capacity expansion planning. If we can capture the variability that matters, we can differentiate between 2-hour batteries, 4-hour batteries, 100-hour batteries, gas turbine needs, ability to integrate SMRs and things like that. It's all a matter of representing that variability in the most efficient way possible. Some people think that means full chronology. We have to have 8760 or 87,600, depending on how many weather years you have. But that gets impractical very quickly, and you wind up throwing out the opportunity to do all those other things well. Include DC power flow, include resource characteristics in detail that can help you model flexibility. So the trick there is to filter down the vast universe of scenarios that we have from historical data and determine what are the ones that are really essential to represent the variability that matters for the resource mix that we're trying to pick between. And we can think about that in the first plot here is that's full chronology. The next one, it would be representative days, which is what most capacity expansion studies would do today. And a third alternative is to think about it from the standpoint of picking the representative states and then connecting them in the same way that you would with chronological representation, but without the weight of the chronological constraints and without the need to have 24 hours to represent a representative day. And by doing so, you can model all those other details efficiently. And with that, thank you for your attention.
All right, I'll leave the cartoon up for a second. Thank you, Russ, for your great thoughts there. So yeah, next we're coming to Tarek Ibrahim, who's the head of advanced analytics at Energy Exemplar. So I think Russ set the stage nicely for the ELCC linkage within a capacity expansion modeling framework. I think, Norm, you mentioned ELCC as a possible signal between capacity expansion and RA. So I think we're gonna have a nice chance to kind of have a deeper dive discussion here on ways that we can use ELCC surfaces in this planning paradigm. So thanks, Tarek.
Thank you.
I guess we can. There you go.
Yeah, so thanks everybody for laying the ground actually for me to go kind of deeper into a specific application, like an automation application or integration application in the energy industry, which is how to derive the multidimensional ELCC surface and use it endogenously within the capacity expansion model using like linearization techniques and multiple segments and so forth. So just to lay the ground, just need to talk about a little bit like what is resource adequacy and how it is basically the ability of the power system to supply enough electricity to always meet demand. And usually it's not a super straightforward calculation because of lots of uncertainties happening in the energy markets coming from like fuel supply risk, weather uncertainties, load forecasts, forced outage rates, so on and so forth. So that's why we do use probabilistic metrics like loss of load expectation or loss of load probability. Some people use like loss of load hours or like expected energy not served, so on and so forth. But the industry standard is usually like a 1 day per 10 years loss of load expectation. And like reliability studies, again, are becoming more critical because of like the intermittent generation, the retirement of the firm capacity resources or the conventional resources, and definitely the correlated generation patterns, meaning like when you lose a generator from a specific technology, if it's conventional, you lose only that guy. But if it's like renewable, it's basically you lose the same technology generators within a specific region or a zone. And that definitely like makes the power system prone to lots of risks. So what is ELCC? Like it's basically the effective load carrying capacity or capability. And it's measured by how much like extra load I can supply if I am actually adding a resource or a portfolio of resources, like either a single resource or a portfolio of resources. And I will talk about like surfaces in a second and why we don't actually like prefer to use like a single resource ELCC and instead we use like a collection of resources ELCC or a whole portfolio ELCC. So why multidimensional ELCC surfaces? And again, because ELCC is not additive. The more you add, like let's say solar or wind to the system, maybe the next like 10 megawatts of added solar will add X of firm capacity to your capacity accreditation. But the next 10 megawatts, it's going to add a fraction of that X. And the more you add, the more of that fraction goes down. So it has basically diminishing returns. And definitely the interaction between technologies matter. So pure solar is different than interaction between solar, wind, batteries, and so forth. So interaction between different technologies matter a lot in coming up with that surface and the capacity accreditation of that portfolio of resources. And the last thing, the surface is not flat. As I mentioned, the derivatives are not always constant. So basically that surface is curved and it's not flat. And that's why it's better to represent it as a surface within a capacity expansion model to be able to capture the proper capacity accreditation of the portfolio mix. So here I'm going to just describe an end-to-end workflow of how to derive that ELCC surface and how we basically use it within the capacity expansion problem. So first of all, we define the penetration levels. So you do have already existing capacity from your various technology types, and you know also the maximum allowable penetration levels for these technology types. So you do have those penetration levels, and you definitely have some values in between. And then in that specific use case, we did use AI because it's definitely better to use all the upcoming and latest technologies. And it made things extremely easy. So we did use AI prompting, like it's basically the platform is Plexos. And we did use like AI agents that are trained against the Plexos data structure, the Plexos help documents, the LP files that actually show the problem formulation, so on and so forth, so that it properly understands your use case and it properly understands your prompt to be able to construct models and even analyze results. And then we build the scenario mix. And here what I mean by the scenario mix is each scenario represents a portfolio of resources. Each portfolio of resources have different penetration levels from different technology types. And then we do create the study objects or the model objects. Each scenario is allocated to a specific study so that we study each portfolio separately or in isolation. And then we run the loss of load expectation simulations. And those are basically simulations targeted at targeted to reach a loss of load expectation value of 1 day per 10 years. And we keep adjusting the load up and down until this convergence happens. And once we query the peak load for that portfolio, we represent or we consider that a peak load as the ELCC of that specific portfolio, and we construct one point in our surface or multidimensional ELCC surface. So again, like the checking convergence, if it's not converging, then we use the bisection algorithm to adjust the load up and down until we reach the convergence threshold of 1 day per 10 years. And then we again query the peak load, consider it as the ELCC of the portfolio, populate the ELCC surface. Every portfolio of resources with different penetration levels will represent a single point in the ELCC multidimensional surface. And once the process is complete, we do have the full surface. We just plug it in the capacity expansion endogenously to come up with the build plan that is like achieving the least costs and also respecting the planning reserve margin constraints. So I'll just like those slides just to describe basically each and every step in the workflow in detail. So this is basically the example prompts we did use to build that small model. So it's like I have solar generators with possible penetration of like values you will specify, similarly wind, similarly batteries, and like I want to allocate the max capacity property for these generators or batteries to those values. I also create like scenario objects, model objects, execute studies, so on and so forth. And again, the output of that is a fully created Plexos database that takes like all those combination of resources or of penetration levels together, construct the model matrix and execute them sequentially for the loss of load expectation simulations. And this is just like the output. As you can see here, the Excel table on your left-hand side, those are like the portfolio compositions. We considered here in that study the call as like a constant penetration value. We don't retire call, we do not add extra call, but as you can see, like different values representing different penetration levels from different technology types and their corresponding ELCC after the convergence of those loss of load expectation simulations. like just like a small introduction to like how we did like converge the problem into the one intent. So we start with just an arbitrary value for the load, and then we run the loss of load expectation simulation. If the LOLE is greater than the value we need, then we basically increase the load. If it's smaller, then we decrease the load, and we do use the bisection algorithm to decrease the number of iterations needed to reach convergence. And then once we are within the convergence thresholds, we basically record the ELCC, which is basically the peak load that this portfolio can serve, achieving the 1 day in 10 years loss of load expectation value. And then after that, we do have the surface, but what should we do with that surface, right? Like it's kind of complex to be able to represent that in a mixed interlinear problem, like a problem, right? So we do use like a feature also that is built in within the Plexus engine, which is called the firm capacity groups, and those firm capacity groups basically will linearize the surface into multiple segments. Each one is represented by a big M constraint and activated by a binary decision variable. So as you can see here, the problem formulation, the objective function is always going to be the same, minimizing the net present value of the total system costs, like the fixed costs, like investment, variable costs, so on and so forth. And then we do have also the ELCC, which is the function of the surface. So every like technology type with its own penetration level is plugged into that function, and the operating segment will calculate the ELCC of that portfolio mix and checks whether it is greater than or satisfies basically the planning reserve margin. And again, those segments are represented as big M constraints and activated by binary decision variables. This is just a representation of the firm capacity groups within the tool. And then like some conclusion and like future work. I'll keep it short here, but of course, I just want to mention a couple of points. With a lot of technologies and like how complex the grids become, those surfaces can, like the dimensions can be extremely large. And that will introduce a lot of binary decision variables in the problem and might impact efficiency. So we did also do some data science exercises to kick out some of those technologies by basically like figure out every pair of portfolios that have constant values for all the technology types except the one of interest. And then for every pair, we calculate the DELCC by the deep penetration level. And if they are fairly consistent, we take them out of the surface and we consider their contribution as a constant value. Also, there is another like idea that I've been working on, which is basically representing the surface as a neural network in the mixed interlinear program, and basically use Gurobi callback functions to basically call that neural network. So we enforce the ELCC constraint or the planning reserve margin constraint as a lazy constraint. So Plexus will just, or like the model will just build the most economic build plan and then plug in the values for that build plan into the neural network. If it does satisfy the planning reserve margin, we're good. If it doesn't, then go and make changes to those values and keep going. So that's all I have. I hope that was digestible. And thank you.
Excellent. Thank you, Tarek. All right, last presenter. Oh, gosh. We're all good. Oh, no.
All good.
Yes, if you ever come up here, it's very narrow behind the chairs, so be careful. All right. Vincent, do you want to come on up? Yeah, good idea. Come to the front. Yeah, well, yeah, okay. Vincent is going to continue with the theme of linking capacity expansion models with resource adequacy, but we're going to do a slight pivot to thinking about weather and climate data and using Earth systems models. So kind of coming back to the theme of weather data that we had earlier today. So he's going to share some results from some work that he's been doing. Thanks, Vincent. Oh, and he is a researcher at the National Laboratory of the Rockies.
Thank you, Bethany, for that introduction. And howdy, y'all. Thank y'all for attending our session. My name is Vincent Krag, and I'm a researcher at the Grid Planning Analysis Center in the National Laboratory of the Rockies. Let me just double check this is working. Cool. Okay. So throughout our session, you've heard our presenters emphasize the importance of both high quality, consistent data, as well as solid linkages between the economic models of power system planning. Today, I'll be showcasing an example of both by presenting on an ongoing project focused on using newly downscaled Earth system model climate projections as inputs for both capacity expansion modeling as well as resource adequacy reliability testing. So in the first section of our presentation, it'll focus mostly on the translation of Earth system model weather projections into capacity expansion inputs and the impacts that these projections have on system results. Section 2 will then focus on the methods for assessing the reliability of these power systems developed in Section 1, using a resource adequacy tool to stress test the non-optimal, or meant to stress test them against non-optimal unseen weather conditions. So let's get started. As you know, there's a ton of uncertainty when it comes to predicting Earth's future weather conditions 10, 25, 50 years from now, as evident by the vast number of Earth system models that have been developed to do just that, each of them having their own set of unique model assumptions that lead to global weather predictions that can vary drastically from one Earth system model to another. This uncertainty can pose a big challenge for power system planners who need to ensure that the systems that they develop today stay reliable in the face of uncertain weather conditions 10, 25, 50 years down the road. Thankfully, advancements in machine learning and generative AI now allow us to take these coarse resolution weather conditions from Earth system models, project them out, downscale them to higher resolutions, and then incorporate them into capacity expansion planning models like REEDS. So let's step through the workflow for Section 1 for incorporating these Earth system model projections into capacity expansion models. First, weather projections from various Earth system models are downscaled to 4-kilometer hourly resolution by the Super CC climate model downscaling tool, and then applied into the various power system inputs. Our capacity expansion model that we use for this project, REEDS, then takes these inputs and then develops different future power systems of the 2050 US power sector by performing a least cost optimization using these weather-informed inputs. We'll then want to analyze these resulting power systems to answer the question, how do the projections from the various Earth system models affect the resulting power system required to meet future electricity demand? So on screen, there are some examples of different weather projections from the ESMs that were translated to power system inputs. On screen here, it shows how US demand projections developed by Evolved Energy Research were adjusted by maintaining annual load but adjusting seasonal peaks to account for the increasing air temperature profiles seen in the 5 ESMs that we used in our study. We also adjusted the resource availability and generation potential of wind and solar technologies using NLR's Rev tool to adjust their capacity factor profiles based on trends in air temperature, wind speed, and global horizontal irradiance seen in the ESM projections. Okay. So on screen are the capacity expansion REEDS results from the different runs that use the inputs that have been weather informed by the 5 different Earth system models used in the study. The bar plots on the right show the 2050 US capacity and generation differences when comparing these ESM-informed systems against a baseline system informed by the reanalysis data. On the left, I've also included the solar and wind capacity factor values from the different ESMs to showcase how their deviations from that baseline, which I think on the Yeah, on the left, you could see as blue stars how their deviations from the baseline affect the reads results. So for example, the reduction in wind capacity factors seen across all of the ESMs used in this study are clearly reflected in most of the reads results seen on the right by the reduced wind deployment seen across these results. In particular, the systems or the ESMs with the highest capacity factor reductions, that being ESM1 and ESM2, clearly show the highest reductions in wind deployment in the reads results. We can also see how the interplay between two or more weather-informed inputs could lead to unexpected reads or like capacity expansion results. In particular, the increased solar deployment seen in ESM1 and ESM2 does seem to contradict the reduced solar capacity factor from these scenarios. We infer that actually the weather adjustments to load, which is driven by mainly air temperature increases, and cause increased summer peaks that benefit solar effectiveness, may be overriding the reduced solar capacity factors seen in these reads results. So based on the results, we can conclude that the incorporation of ESM weather projections does have a notable effect on system outcomes, leading to systems that differ depending on the particular and specific Earth system models that are informing the inputs to capacity expansion. But here's the thing. All of these systems were built assuming correct prediction of the future weather conditions in which they would be operating in. So like, for example, what if we plan the future US power system against the future weather conditions of like ESM1, and then 50 years down the road come to find out that the realized future weather conditions are actually more like that of ESM2? Will the system stay reliable? Reads as a capacity expansion model is only capable of assessing the reliability of the system against the expected weather conditions that it was planned for. So to do something like that would require a different tool for the job. So let's go back real quick to the workflow used in section 1. As you remember, the capacity expansion model took weather-informed power system inputs and then used them to develop different optimized future power systems. We could continue this workflow and employ the use of a resource adequacy tool called PRAS, or the Probabilistic Resource Adequacy Suite, to stress test any one of these ESM optimized power systems against the weather conditions from the other ESMs. This type of stress test would give us the system's net expected unserved energy, which we could use as a proxy for reliability to then answer the question, how reliable would a system designed for one ESM future be when subject to the weather conditions of other weather projections? So on screen are the results of this new capacity expansion to resource adequacy linkage, showing the net expected unserved energy of the ESM1 optimized power system when stress tested using PRAS against unseen weather conditions of like non-ESM1 weather. Highlighted in blue in the table is the initial reliability score of the system of the ESM1 system that was developed by Reeds, which during its optimization enforces a minimum reliability threshold of 1 part per million net expected unserved energy, or better whenever considering an optimized system. So comparing this value of 0.0076 to the stress test results, we can see and can conclude that the ESM system is relatively reliable or decent when against the uncertain weather conditions. When you stress test it against the weather conditions of ESM 2 and 3, you can see that that net expected unserved energy value goes down, indicating a higher reliability to the system. When stress tested against the weather of ESM 4 and 5, that value goes up, indicating that these weather conditions result in lower reliability for the system. We then conducted the same stress test against the rest of the power systems to get the full matrix of results. And then in the next slide, I'll show you how we plan on using this new matrix for to do future analysis. So one of the ways that we could do future analysis is to like analyze the matrix row-wise, assessing the stress test NEUE results against the initial reliability of the system to determine the system's robustness, or in other words, how well it can fare against uncertain weather conditions. This is like basically what we did in the previous slide for ESM1. You can also do a column-wise analysis of this matrix, counting the number of times that the specific weather conditions increase or lower the stress, or increase or lower the reliability of the various systems. So in this example, you could see that ESM5 weather conditions increase the NEUE of the different systems the most number of times out of any of the weather conditions, indicating that these future weather is like the most difficult for power systems to stay reliable against. And then for the purposes of time, I'll be skipping over the third analysis or different type of analysis that you could use or do in this matrix. So ending with the main takeaways, of course, the main purpose of this presentation is to showcase how having high quality, good data and solid linkages across the economic models can lay the foundation for important power sector planning studies. We still have a ton of work that we want to do in this project since it's still ongoing, including that normalized threshold study that I had skipped over and you can ask about in the questions. But there's still plenty more work to be done in this space, and I thank you for your time. Look forward to the questions.
Yeah, good idea.
Great, thanks, Vincent. All right, so we have about 25 minutes for discussion. So I'm going to open it up to the audience to, as like we did this morning, to go to one of the microphones